Hello and welcome to a new video lecture in which we will first discuss the difference between analysis and design problems. So I'm going to carry this discussion in a big table in which we will look at the differences and similarities between analysis and design. So let's draw this table first. And in the left column, we will discuss analysis, and in the right column, we will discuss design. And let's start first with the scope. So what is the reason for doing each of these? Well, an analysis is carried out in order to determine the behavior of a given structure. So we have most of the information of the structure given, and we need to investigate how the structure behaves. On the other hand, a design problem involves the selection of a structural system which can safely resist the loads that act on the structure. In other words, we know the loads and we need to determine the structure such that it can carry the loads, and the key word here is safely. So let's keep on looking at the analysis problem. We are normally given the following information. So we know the geometry of the structure. In other words, we know how the structure looks like. We know the dimensions, we know the configuration, and so forth. We know the member sizes. So we know how big, for example, the cross-section of the members in a truss are, and we also know the material properties. We know what the members are made of, and we know, for example, the yield stress or the modulus of elasticity for those materials. What we need to calculate are either the forces that the structure can support. So how much load can we put on this given structure before the structure would fail? So we need to calculate these forces. Or if these forces are given to us, then one needs to determine whether the structure is sufficient. Or in other words, is the structure capable of carrying the loads? And the answer to the second type of problem would be yes or no. Yes, the structure is strong enough, or no, the structure is not and may collapse. For design, we are given again the geometry of the structure. So we know the dimensions, we know the configuration, we know how the structure looks overall. We know the forces that will be applied, that the structure will have to carry safely, and we know the material properties because we know what the structure will be made of, and hence we know the properties of that material. What we need to find and determine are the sizes of the members in a structure such that the structure can carry the loads safely. The outcome of these two problems is a unique solution for any analysis. So either the result are magnitudes of forces that can be carried by the structure, or whether the structure is strong enough to carry the loads or not. However, for a design question, one can obtain multiple solutions that all of them will be good in the sense that the structure will be able to safely carry the loads. However, for efficiency, one must always select the most cost-effective solution. In general, that means the least mass, the lightest members, because the cost of the members is based on their weight. So these are the main differences between analysis and design. I'm going to tell you a few words about the concept of the load factor. So in order to understand the load factor, let's look again in very brief summary at what analysis means. And by performing the analysis of a structure, all we need to know is the actual force that a structure can carry. So the actual force that the structure can carry, or if the structure can support the given loads. So we need to know the exact number, the exact magnitude of the force, which, if exceeded, the structure would be in danger of collapsing. This doesn't include any additional safety factors. In the case of design, however, when we determine the member sizes, we will have to do so such that the structure can, and the key word is safely carry the specified loads. So we have to ensure that no matter what, the structure will still carry these loads in a safe manner. Now we all know, for example, what the expected loads would be on a structure. And some examples would be the students' weight in a classroom, or the wind loading on a building, or the snow load on a roof. But we know these as typical maximum values. However, under certain conditions, these loads may exceed their values. What if, for example, in a classroom there's a very popular professor and all of a sudden a lot of students show up, and that would exceed the capacity of the classroom. So there are more students in the classroom than they should be in that classroom. Or what if the material strength that the structure is made of may be lower than assumed, just by accident? Maybe only one column has material, or is made of material that is less strong than the rest. The other thing that may happen is that maybe the analysis method that we employed, which is probably not perfectly accurate, may be unconservative, meaning a little unreliable. So in other words, it might tell us that the structure is safe, but it may be not that safe by some small percentage difference. Or the engineer can make possible calculation errors, omissions, and so forth. And all these, even though we would be pretty confident on the design methodology, all these can actually lead to an unsafe design. And remember, the structure must carry the loads safely. So therefore, what is being done in design is the inclusion of a load factor in the design calculations, and this will ensure adequate safety of the design procedure. Now, in order for this to work accordingly, the load factor is typically a number that is equal or greater than 1. For example, typical ranges are given between 1 and 3, and these values are given in design standards. So they're already specified, and the design engineer will obtain them from the design standards and use them in the design procedure. The load factor will be multiplied, will increase the specified loads, and this would lead to what is called factored loads. So the given loads, the originally given loads, are the loads that are specified, The loads increased multiplied by the load factor are the factored loads. And the factor loads are the ones that are being used for design, because we want the design, again, to lead to a structure that can safely carry the loads. For analysis, where we just check the adequacy of a structure, we don't need this extra safety. We just want to see a number, exactly how much force that structure can carry. So therefore, the load factor is always used for design problems, but is not typically used for analysis problems. Very important to remember that. When to use the load factor? Only for design, in general, not for analysis. So having said that, let's see how we can perform analysis and design calculations for members under axial tension, straight members under axial tension, like the members in a truss. So let's do another small table. On the left-hand side, we will talk about analysis. On the right-hand side, we will talk about design. And both methodologies are based on the formula that we've learned about stress. Stress equals to the force divided by the area. So for analysis, we need to calculate the force that the member can support. We can solve for P equals to sigma times the area. And of course, in this case, sigma would be the maximum stress that the member can sustain before it fails. So this sigma would be either sigma yield or sigma allowable or sigma ultimate or sigma fail, depending on the type of material that the member is made of. So in this case, sigma is a property of the material, is the failure stress of the material. Or if we are given the forces and we are asked to determine whether the structure is adequate or not under the given loading condition, then we have to solve this inequality. So we're calculating the actual stress equals to the force divided by the area of cross-sectional area of the member that we analyze, and we check whether this has or has not exceeded the failure stress, sigma yield, sigma allowable, sigma ultimate, or sigma fail. And the answer would be, of course, either yes, and that means trouble, the structure may fail, or no, which means the structure is still able to carry the applied loads. For design now, where we have to determine the member sizes, we will of course solve for the cross-sectional area, which has to be larger or equal than the axial force in the member, the tension force in the member, multiplied by the load factor, because this is a design problem now, divided by a property of the material, which is the failure stress. And that again could be sigma yield, sigma allowable, sigma ultimate, sigma fail, whatever is given in the question, and which is a property of the material. Based on the cross-sectional area required, we can then select an appropriate member size, which has an area, a cross-sectional area larger or equal to what is required. But this has to be only by a small amount. So we're not supposed to select huge members, because those members would be very heavy and they will be very expensive. So for cost effectiveness, we have to select the members that have a cross-sectional area just higher than what we require. So again, this is the methodology for designing members, straight members under axial load in tension, such as the members in a truss. For members in compression, there's a different procedure, and it's a little more complicated because it involves another mode of failure called buckling, and that is not covered in this course. So thank you very much for attending this lecture, and we will continue the design in subsequent lectures.